Hello everyone. So this one is our session number 3 and we are going to see one of the most important topic of the matrices, rank of the matrix. Okay, so rank of the matrix by row echelon form. So that is the topic for the today's session. So yes, we'll start this rank of a matrix. So for the rank of a matrix, yes, we require here elementary row operation. So there are three types of elementary row operation. The first one is the interchange. First one is known as interchange, which is denoted as Ri interchange Rj. So this is actually the notation Ri interest. There is one more notation you can denote Rij. So any one that can be preferred. So whenever we want to interchange any two rows of the matrix, we denote by Rij or Ri interchange Rj. Second is related to multiplication. It is multiply. So if you want to multiply by a non-zero constant to the ith row, we can say Ri is replaced by Kri or just say by Kri. So these are the two different ways of denoting it. So first is about interchange. Second is about multiplication. We can multiply by any all the elements of any of the row by a non-zero constant k. And the last one is related to the addition actually. So it is related to the addition where we say replace the ith row by Ri plus Krj, Ri plus Krj, or simply say by Ri plus Krj. So this is also enough, which indicates the change is in the first row, whatever we are started. So by Ri plus Krj default, there is a change in the ith row there. Okay, so you can multiply all the elements of a jth row by k and add it to the ith row. So that are the three elementary row transformation. So these elementary row transformations are very much useful for us for getting the rank of a matrix. Okay, so these elementary row transformation have one important property, and that property is here. It gives us equivalent matrices. So what are these equivalent matrices? So two matrices are said to be equivalent if they are obtained from the elementary row transformation. Okay, so if one of the matrix is obtained by elementary row transformation from the other, okay, elementary row or column transformation, okay, so that is the equivalent matrices. So we denote the equivalent matrices by this symbol. So this is the sign of equivalence, and we can read like A is equivalent to B. Remember, these matrices not remains equal, they become a equivalent. And what is the most important property of equivalent matrices? That equivalent matrices have the same rank, and because of that, elementary transformations we are using for getting the rank of a matrix. So come to the important article here. So the important article is rank of a matrix. So for the rank of a matrix, we have three definitions, one, two, three. Okay. Out of that, the last definition is the most important. The first two definitions we generally never use for solving the example. Okay. To solve the example, the first definition, yes, the first main definition of a rank. Why? Before we go to the rank, what is a rank? Obviously, okay, so I generally give this example of this rank is a word. The rank, we use the rank in our day-to-day life. Okay, rank mainly used for classification purpose. So yes, many of you have the IMU rank. Okay, so what is that IMU rank? It is based on your marks there, IMU CT marks. So whatever the marks you scored in IMU CT, that gives you the IMU rank. So that time marks is a criteria to get the rank. Here for the matrix we have the criteria, and that main criteria for getting the rank for matrix is largest order of a non-zero minor. Largest order of a non-zero minor is a rank. Okay, we'll come to this. What is this largest order of a non-zero minor with a very simple example? So I will write one small matrix here. Suppose our matrix is say 1, 2, 3, 4. Okay, then I will write 2, 4, 6, and say 8. And then I will write here as -1, 0, 0, 0. Okay, suppose this is the matrix. If you see the order of this matrix, it is a 3 by 4. 3 by 4. Now, our first definition says it is the largest order of a non-zero minor. What is minor? Minor is a determinant. Largest order of a non-zero determinant. Non-zero determinant. So, in this case, if you observe the largest order of a non-zero determinant is a 3 by, is it a 3 by 3? No, let me check. Let me check. So, if we observe what is the largest determinant possible for this matrix, which is obtained by deleting one of the column. If we delete one of the column of this matrix, then we get a 3 by 3 determinant. That is the largest order possible. But if we delete any of the row, for example, if we sorry, we can delete any of the column. If we delete the first column, you will observe the determinant is a 0. Determinant is a 0 for last three column, because one of the row is itself a 0. And if you delete the last column, then also the determinant value is a 0, because the first and second row are scalar multiple of each other. So in this case, for this matrices, you can check the 3 by 3. This 3 by 3 determinant is 0. All 3 by 3 determinants are 0. How many are there? 1, 2, 3, 4. 4 determinants possible. So all 3 by 3 determinants are 0. Then we move to the 2 by 2 determinant, because 3 by 3 determinants are a 0, that is the largest order. So we have to move from 3 by 2 to 2 by 2. Now for 2 by 2 determinant, we have to check. Suppose we delete the last row and two of the columns, then you will observe this last row is deleted and two of the last two columns deleted. So 1, 2, 2, 4 left. So still the determinant is a 0. But if you delete the first row, if you delete the first row and last two columns, you left -2. So I will just show you here. So this only left, this one. Suppose we take this 2 by 2 determinant. So this is this 2 plus 4, 6. So the value of determinant is 6, which is non-zero. So at least one 2 by 2 determinant is not 0. At least one 2 by 2 determinant is not 0. Hence rank of this matrix is 2. So this is a method which is used to check the rank, where we say the largest order of non-zero minor. So in this matrix, the largest order of non-zero determinant is a 2 by 2. Hence the rank is a 2 there. Uh, but actually this definition is a too calculative and little complicated, so we never use to get the rank. So instead we'll use the last definition, and the second definition also is not that much useful. So that second definition is the rank is nothing but it is a number of linearly independent rows of that matrix. So this dependence and independence of the rows is very simple. When we say the two quantities are dependent, if we have the equation between them, for example, if we say the first row is r1 and the second row is r2, you will observe r2 is equal to 2r1. R2 is 2r1. So row 1 and 2 are dependent. But if you observe the first and last row, there is no relation between them. So there are two rows which are independent. There are two rows, you can say first and third or second and third. They are independent, because when one depends on other, uh, so we'll go in the detail later on. But remember this definition, here are two independent rows and the rank is again 2. So this definition is also we never use for calculation purpose for finding the rank. So which is the most important then? So the most important definition that we have is the last definition, and that definition says rank is the number of non-zero rows of a row echelon form. So I will tell you what is a row echelon form. We'll go in the detail for that. But remember, this is the most important definition only, and this definition we use for calculating the rank. So that about the definition of a rank. We'll come to the notation. So a rank we denote by either R of A, row of A, or just by R. So these are any one of the three. This notation can be used to denote the rank of a matrix. Actually, we are going to apply elementary row transformation, and we reduce the matrix like a upper triangular matrix. It's a similar to the upper triangular matrix, which is known as the row echelon form. We'll go in the detail, and then we get a rank. Once we get a rank, actually we can use at a number of places as application. Two of the application is a part of our syllabus known as electrical network and a traffic flow problem. Okay, electrical network and traffic flow problem, that is a part of our syllabus. So here is the row echelon form. In simple words, what I want to tell you, just a minute. When we are given a matrix, what is the row echelon form? Row echelon form is just similar to the upper triangular matrix. Means we have to focus on the diagonal elements. So diagonal element is A11, A22, and A33. Okay, A11, A22, A33. What is our aim? Our aim is to use elementary row operation and make all the entries below this diagonal as a zero. We have to make this zero, we have to make this zero, and we have to make this zero. Once all the entries below main diagonal becomes a zero by elementary row operation, what happens? Automatically, dependent row converts to the zero row. For example, suppose the second row is the dependent row, that becomes a 0, 0, 0, 0. Then you can shift that row at the bottom of the matrix, and it becomes a row echelon form. So you will observe if you convert this matrix to the row echelon form, I will tell you what is the form you are going to get it. So roughly you are going to get this form. So you will get these zeros here. Okay, this will become a zero, but here also zero, and here you may get some non-zero element, maybe 0, 0, 0, 1, something like this. Okay, now you will observe this is the row echelon form because all the entries below main diagonals are zero. So in this case, the zero row, what is the zero row? The last row, this last row is said to be a zero row. Why? Because all the elements of that row are zero. All the entries in that row are zero, then it is a zero row. But second last row is a non-zero row. This second last row, this is a non-zero row because this last entry is a non-zero. At least one element in that row is a non-zero, then it is non-zero row. So what is the rank? Rank is a number of non-zero rows. So first row is a non-zero, second row is also non-zero, so the rank is 2. So rank is 2 because two non-zero rows are there. Third is a zero row. So this is a way we get the rank. There is a difference between upper triangular matrix and row echelon form. So actually, upper triangular matrix we say for a square matrix only, and row echelon we can say for a rectangular matrix. So in the rectangular matrix, you will observe that your diagonal is somewhere here. Okay, it is not from first corner to the last corner. It is A11, A22, A33, and below it we want a zeros. Okay, below that we want a zeros, and that is a row echelon form. We'll come to the examples, then it becomes more clear. So here are few examples of row echelon form. They are already reduced in the row echelon form. You will observe what is the important thing. A11 always should be a non-zero. Only there is a condition on A11. You will observe this A11 is a non-zero, this A11. For non-zero matrix, A11 should be a non-zero, because if the matrix is a non-zero, we can shift that element at A11 position by a elementary transformation. So here is A11. So after A11, yes, the elements can be a 0 or non-zero, it doesn't matter, but below A11 should be the zeros. Below A11 should be 0, and so on there. We'll come to that. So here is the main diagonal, A11, A22, A33. Now the rank of this matrix is a 3 because there are 3 non-zero rows. All 3 are non-zero. Last row is also non-zero. So rank of the first matrix is 3, while the rank of second matrix is a 2 because last row is a 0 row. So rank of this matrix is a 2 because it is in row echelon form again. And the third matrix is also in row echelon form. And you will observe the last row is a 0 row. Second last row is a non-zero row. Hence the rank of the last matrix, third matrix, is also 2 there. Okay, so this is where we get rank. So here are few important properties of a rank. A rank of the matrix is always greater than or equal to 0. Rank of the matrix is always greater than or equal to 0. Only 0 matrix have the rank 0. Only the null matrix have the rank 0. So if we have non-singular matrix of order n, if we have the non-singular matrix of order n, means largest minor, non-zero minor is of order n, because non-singular means non-zero determinant. Hence the rank is n. Okay. Hence the rank is n. And when the matrix is of order m by n, matrices of order m by n, rank of A is always less than or equal to minimum of the rows or the column. Okay, so whatever the minimum we have for the matrix, a rectangular matrix, so the rank will be always less than or equal to that minimum number. So that is the few properties there. They are very trivial properties. It's based on the definition of a rank. Now come to the important part here. How to get the rank of a matrix by row echelon method. Suppose this is the example that we have given a matrix A, and the question is find the rank of this matrix A here. So no need to write this. This is just for your understanding, the first part. So as the matrix is 3 by 3, the rank of a matrix will be less than equal to 3. Okay, so your answer should be less than equal to 3, obviously. So that will be the maximum rank there. Now we are going to reduce the matrix A to the row echelon form, and you will observe how to get this row echelon form. Even though I shown here entire calculation, write the matrix A first, focus on A11, use A11 to make these two entries 0. Okay, in step one, better you do some standard process here. So use A11 to make these two 0. So obviously R2 minus 2R1. R2 minus 2R1 gives us this is 0. Only using A11 we are making 0. R3 minus 3R1, that is another transformation. So you'll observe these two are zeros now. So that we achieved, and you will observe the equal sign is replaced by equivalent, because now this matrix A and this matrix are not remains same. They are equivalent. They are equivalent. So this is the equivalence sign, because the corresponding elements are not equal. Here is a 0, here is 2. Hence they are equivalent. Next step, we have to focus on A22 now. Using A22 only, make below A22 0. Okay. Using A22, make below A22 0. So obviously the transformation is R3 minus R2. And you'll observe we achieved the row echelon form. So the matrix is in row echelon form because all the entries below main diagonal are 0. Below main diagonal they are 0. So it is a row echelon form. How many 0 rows are there? Now you'll observe the last row is a 0 row. There are two non-zero rows. So what is the rank of this matrix? So rank of A is 2, and that is the end of a question. That is the end of question. So if you follow the standard process, like using A11, you are making these two zeros. Using A22, you are making below 0. Quickly, in less number of step, in a minimum number of step, you are getting the rank. Otherwise, if you start to making zeros at random position, then you may require more number of steps there. So better to follow the standard process here. So that about rank. Rank is a 2 here. Example 2 now. So here, what is the order of this matrix? You will observe the order of matrix is a 3 by 4. So what is the minimum? Minimum is a rows. So rank is obviously less than equal to 3 now, because it is a minimum of row and column. So that about the first thing. Rank is here less than equal to 3. And here is a solution. So now what is the problem in this is the condition that we have is this A11 should be a non-zero, but A11 is a given 0. So obviously there is a way to convert it into non-zero, interchange the rows. So just R12, we are done. R12, interchange the row 1 and 2. So this A11 becomes a non-zero now. Now using this non-zero entry, we have to make all zeros uh, below the diagonal in the first column. Obviously, this second row is already 0. Only we require transformation for third row. So R3 minus 3R1. So by R3 minus 3R1, we achieved these zeros in the first column below diagonal. Now we focus on A22. Using A22, we are going to make this 0. So the transformation is R3 plus 5R2. Now easily you will observe below main diagonal A11, A22, A33. Below main diagonal everything is 0. So this is a row echelon form. That's a row echelon form. How many non-zero rows are there? You'll observe the first, second, and third. All three are non-zero rows. So rank is 3. The rank of this matrix is 3, and that is the final answer here. So rank of the matrix is 3. That's one. One last example, we have to find the rank of this matrix again by row echelon method. The dimension is again 3 by 4. So obviously the rank will be less than or equal to 3. So rank of this matrix is again less than or equal to 3. And we'll observe here, the method is use A11 only, use A11 to make in the first column below diagonal zeros. So transformation will be R2 minus 3R1 and R3 minus 2R1. So that is achieved in the step number 1 only. Now in step 2, use A22. Using A22, we have to make this as a 0. We have to make this as a 0. So R3 minus R2, simple transformation. And you'll observe it is in row echelon form. The third row is again a non-zero row. So what is the rank? Rank of this matrix. Rank of this matrix is again 3, because all the three are non-zero rows. So you will observe hardly in 3-4 steps generally you get the rank, provided you follow the process and you will not do those silly mistakes in a calculation. So that about the rank of a matrix by row echelon form. In the next session we are going to see the normal and PAQ form. Thank you.